Yay!
Yay! Okay, now that we've done the electric field from a ring along the axis, now what we can do is build things out of that. Because what happens if, suppose you stack a whole bunch of rings of different sizes from the origin out to some distance, what do you have? You've got a disk. So let's see if we can find the electric field from a solid disk that's charged up to plus Q. And how we're going to do it is we're going to use what we had just done before. We're going to imagine that what we can do is we can integrate a whole bunch of little rings all the way around, where each of these rings, let me write down the result from last time. The electric field from a ring is going to be KQ times Z. Q is the charge on that ring, right? And what we want is some distance up here, Z. We want the electric field at that point. So it's KQZ over, and what we had was R squared plus Z squared to the 3/2. All right, so let's see how we're going to do it. We're going to build the disk out of a whole bunch of rings. We're going to sweep out these rings from the origin out to some distance big R. Well, all of these rings have to be really thin, right? Understand the strategy is we're going to integrate from 0 to R. That's going to be our strategy. So our electric field, and we know already each of these little electric fields is going to be in the Z direction. We already found that last time. So really we're just after the magnitude. I know the vector is pointing in the Z. So the electric field is just going to be the integral, and I want to integrate somehow from 0 to R, where this little ring is going to have a radius R, and then there's the little distance from a bit of the ring to the point I'm interested in, right? So I want to integrate these rings. Each ring is really, really thin, and the total charge of the disk is plus Q. So each of these rings now is going to be dq. It's going to have a little bit of charge because they're so thin. So I want to integrate these rings. So I want to say it's K dq times Z over, it's the same business, R squared plus Z squared to the 3/2. Okay, so I want to integrate the electric field. I want to add up the electric field, which we already found, from all of these little rings, from 0 to R. Neat. Here's the problem. I want to go from 0 to R. Well, what's in there right now is dq. Charge doesn't go from 0 to R. The radius, the radii of these rings does. So again, I'm going to need to use a trick. I need to convert from dq to dr. I need to find a relationship between q and r. And again, we're going to use the same kind of ratio trick that we did last time. So here it is. Here's the trick. I'm going to say that a little bit of charge, in other words, the charge of a ring compared to the whole charge of a disk, what is that like? What's that a ratio of? It's like the area of a ring compared to the area of a disk. Let me write it out. Area of ring compared to the area of the disk. Goodness sakes, I ran those words together, didn't I? Area of a disk. Okay, like that. So that's the ratio I'm interested in. And that is, let's see, dq over q is, okay, well, the denominator is easy. What's the area of the disk? Pi big R squared, right? That's the easy part. What is the area of the little thin ring? How am I going to write that? Involving dr. Well, if the ring is really thin, it turns out I can get away with this. What is the area of the ring? It's like the circumference of the ring, right? Multiplied by its thickness. The circumference multiplied by that little bit of thickness is going to give me the area. So what's the circumference of the ring? It's going to be 2 pi r. What's the thickness? Well, the thickness is the thing I want. It's my dr, right? That's the little bit of thickness as I go out in distance. So 2 pi r dr is the area of the ring. And so that's it, right? That's the area of the ring divided by the area of the disk. I think I'm done. So let's see, here the pi's are going to cancel. So this means that my dq is going to be 2q over r squared r dr. Neat. So that's what I can plug in. So I'm going to take this and plug it right in there. And now I'm going to have an integral that's the right form to do. So I'm going to have my dr is going to be my integration variable. Very cool. So here we go. So E is 0 to big R. What have I got? 2kq over r squared. Those are all my constants, and those are going to come outside the integral. Let's see. And then I'm going to have, I got to have my z. That's going to come along outside the integral because that's not changing. And then I've got my r dr over r squared plus z squared, the 3/2. Okay. I see something I need to fix. Maybe you see it too. What is, okay, back here, look at that. That's the size, that big R, I have to be careful. When I wrote down the electric field due to a ring, that's the size of that ring, right? The radius of that ring. And when we were just doing a ring, that was a constant. We just called it big R, right? But now big R is the size of the entire disk. What is the size of each individual ring that I'm summing up? Each individual ring is little r. There we go. So I've got to fix that. That's the right thing. Because as I sweep out this disk, those rings are changing size, right? That's not going to be the same size for every ring. That's part of the integration. Okay, so it looks like that. Okay, so just to be clear, that's going to be 2kqz over r squared, and then I got 0 to r, I have r dr, r squared plus z squared, 3/2. All right. So now I just have to do that integral. You know what? We could look it up. But, integrals that are what are called elementary, sometimes it's kind of fun to do. If it doesn't take up too much extra time, it's fun to just sort of get that back into your head, how to do at least pretty simple integrals. This one, it doesn't look maybe that simple, but all I mean is I can do it with a pretty simple u substitution, right? So let's just for fun, we're all here for fun. So let's see, that's fun. Let's say u is r squared plus z squared, because what I really like is to have something to the 3/2 down there, right? So let's call that u. So my du is going to be what? Just 2r dr. That's my du. I've got that. Look, here's my r dr. There's my r dr. Very cool. So that r dr is just du over 2. So if I substitute this in there, if I make my u substitution, I've got my du on top. All I have to do is r dr is just du over 2. I just need to bring that 2 out. That'll cancel that 2 out in front of the integral, won't it? So I've got this. So I've got, let's see, that'll just be kq z over r squared. And I'm going to, okay, let me just write it down. This is going to be du. On the bottom, I have u to the 3/2, right? So that's just going to be u to the minus 3/2. There we go. That's my integral after the u substitution. That's not so bad. We already know how to do that. Now, the mathematicians are going to start yelling at me because I still have my limits as 0 to r. Shouldn't I change my limits when I do the u substitution? Yeah, I guess. But I don't know. We physicists, we do what we want, right? I don't. Let the mathematicians, I'll block them. Let them come after me. So I'm going to keep it there because what I like to do is then do the back substitution whenever I evaluate the limits. So I'm not going to worry about it. I'm just going to solve it and then I'll back substitute before messing with the limits. So I don't care. I'm just going to keep it like that. All right, what is something to the minus 3/2 power? I'm going to integrate it. So what's the rule? The rule is I increase the power by 1 and put it in the denominator. So this is going to be, so that's going to be like integral of u to the minus 3/2 is like u to the minus 1/2 over minus 1/2. What is that? That is minus 2 over square root of u. Okay, so that's my integral. That's the result of my integral. Okay, so that's going to be, I'll just do it right here. So the electric field is what I got, kqz over r squared. And what I've got is, I have my, oops. Let me bring all my constants out. I got my minus 2 out here, don't I? Minus 2 kqz over r squared. And then I've got my over square root of u. What the heck was u? U was r squared plus z squared. So it's 1 over square root of r squared plus z squared. And now I put my limits back in, right? So now I'm going to go 0 to r. Okay, so now let's put those limits in. I'm going to have e is minus 2kqz over big R squared times. All right. So, sorry. What I need to do, that was little r, not big R. That was dumb. Okay. So now I'm going to put that. I'm going to put that r in. So now I get square root of r squared plus z squared. And then when I put in 0, what have I got? This is going to be minus the other limit, right? So what happens if I put in 0? If I put in 0, I get 1 over square root of z squared, and 1 over square root of z squared is just 1 over z. So this is minus 1 over z. Here we go. I can simplify that a little bit. First of all, there's too many minus signs. I don't like it. So let me put the overall minus sign. I'm going to bring that inside. So I'm going to flip-flop the order of the things that are subtracted, right? And then what I'm going to do is multiply the z in. It's going to make it look a little bit nicer. So all I'm saying is, okay, let's flip the order of these things. I'm going to have 2kqz over r squared. Oops, I said I was going to move the z in, didn't I? Take that out. If I move the z inside and flip the order, this is just going to make that a 1 minus z over square root of r squared plus z squared. Okay, and I think that's it. This is it. This is the exact answer. Here is the electric field of a disk. Nice. And all we did, we built it out of what we knew about rings. We just built it out of the integration of the rings. Is it right? I mean, maybe. It looks like kind of a complicated expression. So one thing we could do, like we did before, is check the limits. Let's check its limits and see what we get. I mean, certainly if you know the charge Q of the disk and you know the size of the disk R, big R, and you know their distance away from the disk, you just plug in numbers and you can find out what the electric field is. But let's see if this thing makes sense. And how did we do it last time? What we said was, I mean, if you have a little disk like a quarter or something and it's charged, what does it look like if you're half a mile away from that thing? Well, if you go really far away, it'll look like a point charge, right? So here again, this should be a function that when you go really, really far away, this thing should look like a point charge. Well, it sure doesn't look like a point charge now. So let's see. Let me rewrite it on this page. E is what the heck was it? 2kq over big R squared, and we had a 1 minus a z over what was it? It was r squared plus z squared, right? R squared plus z squared. I think I wrote it down. Yeah. Okay, cool. All right, that's what it is. So far away, let's see what happens far away. So far away, what do I mean? I mean when your distance is way bigger than the size of the thing. Okay, so if I let z be a whole bunch bigger than r, then what do I get in the denominator here? In the denominator here, I forgot I have this neat laser pointer. That's kind of cool. So in the denominator, if I let z be a whole bunch bigger than r, then this term dominates. And so then I would just have the square root of z squared. That's just z, right? So that would just wind up being z over z. It's like 1. And what I get is like 1 minus 1, and that's like 0. Okay, so what is that telling me? That tells me that if I go really, really far away from this thing, it's going to look like the electric field is going to go down to 0. Well, I know that. I know that's what electric fields do. A few problems ago, what we said, I think it was for the dipole, right? What we said was, if you do a test like this and you're getting 0 out of it, it's not a sensitive enough test. So let's look at it more carefully. And how did we do it more carefully? We use the binomial approximation. So we can't do something this simple, apparently. We need to be a little bit more careful. So can I get that thing down below? Remember, binomial was trying to get things in this form. 1 plus x to the n is about 1 plus nx. That's sort of a crazy, useful, magical thing. But x has to be small compared to 1. And then this works. All right, so let's see. How can I make that really, really small? Well, one thing I could do, it's that square root term that bothers me. What I can do is I can factor out a z. Let's take that z squared out, because I want that leading 1, right? So divide both of those things by z, so I get this 2kq over r squared. What if I have 1 minus z over, take that z squared, like divide both of those terms by z squared, and what you're going to get is, and then the square root of that thing is a z, right? So I'm going to have a z on the outside, and then in here I'm going to have a 1 plus r squared over z squared. Just imagine taking the z inside, so you multiply everything by z squared, and then you get what we had before. So sort of reverse it, and that should make sense. So let's do that. And then what you're going to notice is those z's cancel. And r squared over z squared, is that small? Yeah, because we said that z is a whole bunch bigger than r. So that's going to be a tiny thing. So the square root, 1 plus r squared over z squared, is approximately, oh, this is to the 1/2 minus, sorry, the square root's in the denominator, right? So this is to the minus 1/2. I just bring that minus 1/2 inside. So this is just going to be 1 minus r squared over 2z squared. That's going to be a lot easier to deal with. Okay, so I've got 2kq over r squared, and look what I have. 1 minus this thing. 1 minus 1 minus r squared over 2z squared. Okay, approximately, to be fair, but that's fine. Oh, look how easy this is. 1 minus 1, 0. Minus r squared, the minuses go away. The r squared is going to cancel that r squared. The 2 is going to cancel that 2. What? Look how great this is. kq over z squared. Boom. We got it. So using this more sensitive test, it is true that if I go far away from this thing, far away from this disk, that the electric field really does die down like a point charge. This thing really does look like a point charge when you get far away from it. Really neat. That's really cool. How about when you're close? If you're close, this means that z is way less than r. Right? So go back up here and look at our expression up here again. If z is way less than r, then what have I got? Then I have 2kq over r squared, and then I have 1 minus, well now, the r squared is the term that dominates. So that's just going to be z over square root of r squared, so z over r. Like that. But look, z is much less than r, right? R is a whole bunch bigger than z. So compared to 1, this term is negligible. So I just have approximately 2kq over r squared. So as you get close to the disk, as the disk, another way of saying it, it's an infinite disk, what does the electric field look like? It doesn't depend on distance at all. There's no z in there. This is a constant. A constant electric field, so it doesn't decrease with distance. That's really neat, and we're going to use that a lot. In fact, how about this? What if I say this? If you're close enough to a disk that it looks infinite, it's any shape you want it to be, right? It might as well be an infinite sheet or an infinite triangle or an infinite rhombus or whatever. You don't care, right? Because you can't see the edges if it's infinite. So this is also the electric field from an infinite sheet of charge if you get really, really close to it. That's really neat. And it's still pointed in the z direction. So the electric field is still from a sheet. The electric field is still from a positively charged sheet. It's still coming off perpendicular to the sheet in that z direction. But if you get close, it's constant. It doesn't depend on distance. That's going to be really valuable for us to have a uniform, constant electric field. In fact, it's so useful, we're going to write it a different way. Because, I mean, think about the way that I wrote it is a little bit weird. If it's an infinite sheet, then what does the r mean? Right? It kind of loses meaning. So if it's a really, really big sheet, what we do is this. How about this? This is a neat little trick. 2kq over r squared. What if I do this? What if I multiply the top and the bottom by pi for seemingly no reason at all? Well, then that bottom, q over pi r squared is the area, right? And q over the area is going to be defined as this new thing. That's charge per unit area. That's like a charge density. Q over area is what we're going to write in the future as this lowercase Greek sigma. This is sigma. This is surface charge density. It's just coulombs per square meter. It's what it sounds like it is. But it just makes writing things a little bit easier. So the electric field, if I do this, is just 2k pi sigma when you're close to the disk. And a little bit easier way to write it down, it turns out, remember what that k was? We haven't used it much yet, but remember k is defined in terms of another constant called 4 pi epsilon naught. So if we put that in there, the 2 pi and the 4 pi kind of cancel, and here's what we get. A very simple thing. Oops, 2. Sigma over 2 epsilon naught. Oops. It didn't make a neat box. Let's make a neat box. It didn't make a neat box. There we go. I have to call up the box tool. So when you're close to a sheet, an infinite sheet of charge, whether it's disc-shaped or triangle-shaped or whatever, it doesn't matter. If you're really close to it so that it looks infinite, the electric field is the surface charge density divided by 2 epsilon naught. It's just a number. It's just a number. Charge per, and sigma is charge per square meter. That's really neat. We're going to use that. That's what we're going to use to build devices in the future called capacitors and things like that, where you have uniform electric fields. Or we're going to investigate the electric fields close to the surfaces of conductors in more detail. So we're going to use this result over and over and over again. Very, very, very cool.